Good evening, everyone. We are in the week 12 problem solving session of the NPTEL course Network Analysis, and week 12 is about ideal op-amp circuits. I am Teja Golla, a fourth year research scholar working under Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Can you see my screen?
Yes, sir.
Okay. So this will be our last week, which is about ideal op-amp circuits, which is also very simple, and the problems are also very simple. You just have to understand the basic fundamentals of op-amp. So I'll touch upon the fundamentals before we solve any problems. And also there will be one additional 1 hour lecture, which will be like a doubt clearing session, or I could summarize what all we have discussed in this entire problem solving sessions. So that will be on Wednesday, 7 to 8 p.m. in the same link. NPTEL team will soon share the details regarding that, but I think they'll share tomorrow. I'm just telling you ahead. So I'll just quickly mention about what is an ideal operational amplifier. So we will be dealing with only ideal op-amp that is only there in the syllabus. What if it's an op-amp that is beyond the core syllabus? So that we'll not be discussing today. So we'll only be discussing about ideal op-amp. Op-amp is nothing but operational amplifier. It is also called as op-amp. So if you consider it's a physical IC, right? So people use op-amp in their circuits. So it will be something like a box. It will be something like this. And it has 8 pins. The most famous one is the IC741, which is Texas Instruments op-amp. Texas Instruments is the company who manufactures this op-amp. So basically it is like a IC which has 8 pins. And whenever we say IC, so say it is symmetric. How will we know which is pin 1, which is pin 2? So usually they put a dot here, or sometimes there will be a notch here. So that notch or this dot shows that it is the top side. So then the pin numbers will be something like this: 1, 2, 3, 4, usual. Again from bottom, 5, 6, 7, 8. And today's our point of interest are only few pins, which are the negative terminal, negative input terminal, or inverting input. And then this is minus VDD, and this is plus VDD, and this is the output. So we are only interested about these 5 pins because whenever you see any op-amp, we'll represent it by something like this, right? So this is minus, this is the plus, and then we also have the positive terminal over here and the negative, and this is the output. So this will be our plus VDD. This is our minus VDD, and this is the output, and this is the negative terminal, and this is the positive terminal. Inverting and non-inverting inputs. And if I write the numbers, so this is the pin number 8, and this is pin number 4, this is pin number 6, this is pin number 2, and this is pin number 3. So usually you see the right side picture in most of the diagrams because that is a simplified form of writing it. But in practice, whatever IC we will get, IC741, which is one of the famous op-amps, most of you might have seen it in the labs that you have worked if you have worked on any op-amp based experiments. So they'll be using IC741. And these are the terminals that are of our interest. So this is how basic op-amp looks. And op-amp is an active device. Active device means it needs external power supply to work. So let me also write that down. So it's an active device. Which means it needs external supply to work. So if you see what is the external supply here, it is the plus VDD and minus VDD. So if you don't give plus VDD minus VDD and just give input, you will not get any output. So that's why it is called active device, which means it needs an external supply. So now if I ask what is a passive element, say re resistor, capacitor, you just give input, you will get output. You don't have to give any additional supply as such, right? By just giving input, you will not get the output in an op-amp. You have to give plus VDD minus VDD in addition with the input. But whereas in the case of resistor, capacitor, inductor, you just have to give the input and you will get output. Say you excite it with voltage, you will get current. Or if you excite it with current, you will get voltage. There is no external supply needed. So now if you see the input output characteristics of an op-amp. So basically we are drawing the input versus. So this is how it looks. So if I call this uh, as V naught, and if I call this V positive minus V minus, or let me give these numbers. So let us call this V1. So let us call this input as V1 and let us call this as V2. So positive terminal is V2, negative terminal input is inverting terminal is V1. So, and let us say V2 minus V1. So we are checking the differential input, which is positive voltage minus the negative voltage, V2 minus V1, and then checking the output. So it usually exhibit this type of behavior. So this is plus VDD and this is minus VDD. So whenever it is linear, this region is called as linear region. This is called linear region. And the slope is given by A, which is also called as the gain of the op-amp. So this is called gain of the op-amp. Okay. So in that region, output and input are linearly related. So V naught equals to A into V2 minus V1. And once it exceeds a certain range, then it will be saturated to plus VDD on the positive side and minus VDD on the negative side. So this is basically a non-linear op-amp. So if it is, so not non-linear, non-ideal op-amp. If it's an ideal op-amp, then this linear region will be vanished. We'll see that in some time, but this is basically non-ideal op-amp. Okay, so I can write something like this. So it has basically three regions, right? So let me write V naught is equals to, okay. So there are basically three regions. First region is plus VDD. Then we have A into V2 minus V1 and then minus VDD. So when is this going to happen? When V2 minus V1 is greater than VDD by A. And when is this going to happen? Minus VDD by A less than V2 minus V1 less than VDD by A. And this happens when V2 minus V1 is less than VDD by A. So, depending upon the input, where it lies, the output is varying. So, if the input is in the second region, it will be just a scalar multiple. If it is in any other region, it will be either clip 2 plus VDD or minus VDD. This is for a non-ideal op-amp. So, if you see the electrical equivalent circuit of this, it will look something like this. So, we have an input and there will be an input resistance. Then the output is something like this. There is an output resistance. So this is my V1 and this is my V2 and this is some input resistance non-ideal and this will be A into V2 minus V1 and this is R0 and this is plus minus V0. So in that linear region, so this basically is only for that linear region. So in that linear region, if you see there is no output connected V0, then V0 is nothing but A into V2 minus V1, right? Agree? Everyone? Hello? Here in this case, it is A into V2 minus V1, right? V0? Yes. And because it is non-ideal, it has some input resistance as well as the output resistance. So we basically start with non-ideal op-amp and then now we'll see what happens for an ideal op-amp. So if we are talking about ideal op-amp, okay. So now let us talk about ideal op-amp. In the ideal op-amp, input impedance or input resistance becomes infinite. So it is basically like an open circuit and R out will become zero. So basically it is shorted at the output and the gain is also infinite. So compared to non-ideal op-amp case, if we are talking about the op-amp case, then this is what is going to happen. Is this clear until this point? I have just touched upon the op-amp circuits. What are the important terminals? Then I have mentioned what are the input-output characteristics of a non-ideal op-amp. And then we have divided it into three regions. And then we have seen what is the input-output regions and their voltage boundaries. And then we have seen the circuit, electrical equivalent circuit of a non-ideal op-amp. Now we'll be going and see how the ideal op-amp circuit looks like. Yes. So if you don't have any queries, now let us move to ideal op-amp. So now we are talking about ideal op-amp. Okay. So in the case of ideal op-amp, first of all, if you see here, A is infinite. So now this will not be like this at a, it will not be like having some slope. The slope is infinite. So it will be a vertical line. So let us redraw the circuit, not the circuit, let us redraw the graph again. So we'll get something like this. And now we know this is minus VDD and this is plus VDD and the gain has become infinite, right? So that's why it become vertical. And this is my V0 and this is my V2 minus V1. So now basically if I again now the three regions has become two regions because that linear region has vanished because of the infinite gain. So now if I write my output, has two terms. One is plus VDD, one is minus VDD. So plus VDD happens if V2 is greater than V1, and this happens if V2 is less than V1. So we have only two regions, and this is what we are going to deal with today. We'll only be discussing about the ideal op-amps. Agree? Everyone agree? Is this clear until this point? Yes. Okay. Now, if we check V2 minus V1 expression, now if we check V2 minus V1 expression, it is nothing but V naught by A. And we know that A is tending to infinite. So then what happens to the value of V2 minus V1? If A is tending to infinite, V2 minus V1? V2 equals to V1, 0. Yes. So from this, we'll get V2 equals to V1, which means the negative or the non-inverting terminal and the inverting terminal both are having the same potential. So this is also called as virtual short. Okay. And this happens only in the case of ideal op-amp. And as far as this course is concerned, we are dealing with this. So you can consider in any problem, there is virtual short, and then using that, you can solve. So if you have any doubts, you can ask. Now we'll deal with some standard circuits called inverting amplifier, non-inverting amplifier, and differential amplifier. So we'll be using this result VT equal to V1, and then we'll see how we'll get we'll try to understand inverting, non-inverting, and differential amplifiers. So we can proceed, or do you have any queries? No queries? Okay, someone has mentioned no, sir. Okay. So now we'll start with the inverting amplifier. And whatever we'll be discussing three circuits today, and these are very much important. So no matter whatever you do in the future, if it is anywhere related to circuit, this knowledge is very much important. So this is very fundamental. Please pay attention. If you have any doubts, please ask. So we have minus and then plus. So the circuit looks something like this. So this is resistance R1, this is R2, and this is V0, and this is V input VI. So, so because input resistance is infinite, it also means input current is zero. Because input resistance is zero, as if here it is open, right? So the current drawn is basically zero. So input current is equals to zero for ideal open. Input current equals to zero, meaning this current is zero. This current is zero. Agree? That is the input current, because the input impedance or the input resistance, whatever is connected, it draws zero current. Basically, I can put a resistor here, which is infinite. So it doesn't draw any current. Basically, it is like an open. So it doesn't draw any current. Now, from the concept that we have learned, V2 equals to V1. This terminal is also ground, right? This terminal is also ground, right? Because minus and plus are virtually shorted. Agree? because both are having the same potential using this virtual short concept. Okay. So now, because the current is not flowing in that direction, I will highlight something. So the current in this branch will totally flow through this branch, right? Whatever is the current flowing through R1 must flow through R2 because KCL should be valid, right? So let us assume the current is flowing in this direction. So from left to right, say from Vi to 0 and from 0 to V0. So now can you apply KCL and let me know what will be the equation that we'll be getting? Because there is no other path for the current to flow, it will only flow in this direction. So I can consider the current through resistance R1 is same as current through resistance R2 and the direction of the current is from left to right. So can you please tell me what is the KCL equation that we'll be getting? Anyone? Current through R1 equals to current through R2. So what will be the expression? Okay, so someone says, Jnanendra is saying V1 minus 0 by R1 equal to 0 minus V0 by R2. Yeah, very good. So basically current flowing through resistance R1 from left to right is nothing but Vi minus 0 by R1 and current flowing through R2 from left to right is 0 minus V0 by R2. So from this we'll get V0 is nothing but minus R2 by R1 into Vi. Agree everyone? If you see there is a minus sign here. So that's why it is called inverting amplifier because output is having a minus sign of the input. So if input is positive, output is negative. If input is negative, output is positive. So that's why it is called inverting amplifier and the gain is R2 by R1. So I want unity gain, then I can consider R1 equal to R2. If I want gain 2, then I can consider R2 equals to 2R1. So I can get a wide range of gains, but note it is inverting amplifier. So is this circuit clear? Can we proceed further? And you have to remember the circuits, not for this course, but it will be helpful in your future. So remember the circuits, what is inverting amplifier, what is non-inverting. So now let us go to non-inverting amplifier. Okay, so non-inverting amplifier, the circuit looks something similar, but not exactly the same. So now resistance connection, everything remains same. Now input we are giving here and that minus terminal is grounded and then everything else remains same. So input we instead of giving here, we are giving here and ground we are giving it here. So basically if that is Vi, this is also Vi, right? Because of the virtual short concept. And let us assume the current again is flowing in the same direction. So current is flowing in this direction. Same. We are free to choose any direction. So I am assuming the same direction just so that both will be considered in the same convention, nothing else. We can consider the other way around also. So now what will be the expression for KCL? Just similar to this. KCL expression. Anyone? So Nandini says 0 minus Vi by R1 equal to Vi minus V0 by R2. Very good. So if I write it, 0 minus Vi by R1 equal to Vi minus V0 by R2. So solve for Vi. Solve for V0 in terms of Vi. And once you solve, you will get something like this. V0 equals to 1 plus R2 by R1 into Vi. So can anyone confirm if you are getting the same expression? Yes. So Yanandar says Vi into 1 plus R2 by R1. Okay. So now I have a question for you. So what should be the values of R2 and R1 to get a gain of half? Say I need gain of 0.5. So V naught by Vi should be 0.5. And what should be the value of R2 and R1? And let me know if it is possible to get gain half or not. So I need gain half. What should be my R2 and R1 values and whether we can get such resistances or not. Okay. So someone says, no, sir, not possible, I think. Nandini says not possible. What about others? Gyanendra and Parvatam say if I want gain of half, what should be the values of R1 and R2? Parvatam says yes, sir, possible. Okay. So what should be my R2 and R1 values? Uh, Parvatam, can you calculate what will be the values of R1 and R2? Not possible because one is there. Yes. So if you see, this gain can become zero point 0.5 if any of these R2 and R1 are negative, which is not possible. And R2 by R1 is positive and it is 1 plus R2 by R1. So gain is always positive. So here gain gain is always greater than or equals to 1. Gain less than 1 is not possible in this case. And that is something very important. We cannot get gain less than 1 in the case of non-inverting amplifier. Instead, you can connect two inverting amplifiers so that it will become plus. And then gain of one into gain of another, you have to ensure that gain is less than 1, which can be done. But using non-inverting amplifier alone, you cannot get gain less than 1. But can we do in any other different way so that we can get similar gain, but here plus sign? So that is what we are going to see now, which is also called as a differential amplifier. So if you see the above two examples, the input is single-ended, which means we have a single input, either on the positive terminal or on the negative terminal, and the other terminal we have connected to ground. Now we are saying differential amplifier, so there will be two outputs, and the difference of it will be amplified. So let us see. So this is our open. Open. So this is our minus, this is our plus, this is R1, this is R2, this is also R1, and this is R2. And these are our inputs, which are V1 and V2. Now we have to get V0 in terms of V1 and V2. First of all, I know that say this terminal voltage is VA, this terminal voltage is VB. Very first thing I know is VA equals to VB. So this I'll consider equation 1. And I also know the current entering here is 0, current entering is 0. So can you tell VB in terms of V2, what is the value of VB? in terms of V2? What is the value of VB in terms of V2? You can apply KCL and just or any other formula and let me know what will be the expression. So Nandini says VT equal to R2 by R1 plus R2. Sorry, it is VB. So VB equal to R2 by R1 plus R2 into V2. So we'll get VB is equals to R2 by R1 plus R2 into V2, which is also equals to VA, right? Everyone agree? All of you? This is what we'll be getting. First, I'm calculating VB. Yes. Okay. So now VA equals to VB. So now I'll apply the same case here, and the current is flowing in this direction. So what will be the expression of my case here? So Gyanendra Singh says V1 minus VA by R1 equal to VA minus V0 by R2. Yes, very good. So the equation is V1 minus VA by R1 equal to VA minus V0 by R2. So now what you are going to do is you substitute this in this expression and solve for V0 and calculate and let me know what you will be getting after substituting this. So the math is simple, but I just want you to give it a try. So let me know the expression for V0 in terms of V2 and V1. So simplify it everything, bring everything on one side of the equation, keep V0 on the other side and solve for V0 and let me know. Let me know the value of V0. Bring everything on one side and then substitute VA and then you'll get it the idea. I need V0 in terms of the V1 and V2. Anyone? Are you solving? Nandini, Parvatam, Yanendra, and Avinash. Parvatam says R2 by R1 into V1 minus V2. Nandini says R2 by R1 into V2 minus V1. So kindly check, Parvatam, it will be V2 minus V1. So V naught is R2 by R1 into V2 minus V1. So non-inverting terminal minus inverting terminal. So here also we are getting a positive gain. And now gain can be greater than 1, less than 1, or equal to 1 as well, which is not possible in the case of non-inverting amplifier. So let me just quickly summarize. So this completes our theoretical aspects of an op-amp, which is very simple. We just have to understand the virtual short concept and then apply KCL, KVL to solve for what is asked in the question. Okay, let me quickly summarize what we have discussed today in op-amps. So today we'll be dealing with ideal operational amplifier, which is also called as op-amp. So here I have considered one IC741 device which consists of 8 pins, and these are the 8 pins. Out of these 8 pins, our point of interest are only 5 pins, which are the inverting terminal, non-inverting terminal, minus VDD, plus VDD, and output. I have also drawn this circuit, which is usually drawn in the case of circuits. Rather than drawing this complicated 8-pin device, we'll draw this 5-pin device. And minus is called as inverting terminal, plus is called as non-inverting terminal. This is plus VDD, this is minus VDD, and this is the output. And it is active device because it needs external supply to work. And first we have discussed about the input output characteristics for a non-ideal op amp, and it has saturation region as well as the linear region. And the slope of the linear region A is called as the gain of the op amp. And depending upon the difference between the input, output can be minus VDD or A into V2 minus V1, or minus VDD or plus VDD. So we have three options: plus VDD, minus VDD, or A into V2 minus V1. And if we draw the electric equivalent circuit of this, it is something, it looks something like this. And this for linear region, and we notice A into V2 minus V1. If we consider the ideal op amp, input becomes infinite. So this is kind of open. So input current is 0 and output is 0. So basically output is shorted and A is tending to infinite. So if we redraw the input output characteristics, it will look something like this. So if V2 is greater than V1, it is output is plus VDD, else it is minus VDD, and we'll have only two regions because the linear region has vanished because of the infinite slope. Now that slope is infinite, we'll get V2 equals to V1, and it is also called as virtual short. So now using this virtual short, we'll discuss about a few amplifiers. Coming to the first amplifier, which is the inverting amplifier. This is how it looks, and if you apply virtual short concept and then apply KCL, you will get V naught equals to minus R2 by R1 into Vi. And because of this minus, it is called inverting amplifier. And here the gain can be greater than 1 or less than 1. Basically greater than -1 or less than -1. Now when we come to the non-inverting amplifier, this is how the circuit looks, and the output expression is V0 equals to 1 plus R2 by R1 into Vi. And here gain is always greater than or equals to 1. Gain less than 1 is not possible because of this one sign. Now we have discussed about the differential amplifier, where we have two inputs, and this is how the circuit looks. And V naught is nothing but R2 by R1 into V2 minus V1. Say V2 minus V1 is some input voltage Vi, then V0 equals to R2 by R1 into Vi. So gain can be less than 1 or greater than 1 as well, which was not possible in the case of non-inverting amplifier, which was possible here, but it is inverting. So this is non-inverting. Also, it has gain greater than 1 and less than 1 options. So there is less than a minute. If this meeting ends, kindly join back. If you have any queries, you please ask, else we'll start solving the problems. Any doubts until this point? Anyone? If this meeting ends, kindly join back. Any doubts? So this week problems are also very simple, and you can again score maximum marks to compensate for what you have made mistakes in the earlier weeks. So while solving, please do not make any mistakes, and then you can solve all the problems easily. And I'm pretty sure that you'll be able to score full marks if you don't make any mathematical mistake. Okay, so this is our question one. They are asking, they have given one circuit and they're asking what is the value of V1. So anyone, how to solve? Any idea? How to proceed? So they have given some kind of circuit, and they are asking what is my V0. So anyone how to solve? How can we proceed? Any idea? Any thoughts? At least how to proceed? Like what that we have learned till now can be used in this to start the problem. No idea? So like differential amplifier. Okay. Okay. One thing I'll tell, don't mix it with these amplifiers because it might or might not be an amplifier. One thing I wanted to highlight is not every problem can fit into all these three because this is a final result that may or may not be used in a this circuit. So that is one thing you have to keep in mind. So Nandini says virtual short, so 1 volt at the intermediate node. Yes, very good. So basically we'll be using this result, which is the virtual short. It is independent of any circuit. If it is ideal, then we can use virtual short. So this is 1 volt. So this terminal is also 1 volt. Agree? So if this is 1 volt, what will be this voltage? The this voltage? This voltage? Anyone? What will be that voltage? Minus 2 volt. So Parvatam says minus 2 volt. So this will be minus 2 volt, right? Everyone agree? Because the top terminal is 1 volt, this will be 1 minus 3 volt, which is minus 2 volt. Okay. So now can you guess or can you calculate and tell me what is the current flowing in this direction through 5 kilo ohm? So Gyanendra says V naught is minus 1. Let us check whether he's right or wrong. So what is the current? What is the value of I? Any guess? What will be the value? So minus 10 amperes. Parvatam says minus 10 amperes. Everyone agree? What are you getting? Parvatam, are you sure? Is it minus 10 amperes? How did you get minus 10 amperes? Hello, current through 5 kilo ohm. Anyone? 10 amperes. So also says 10 amperes. How are you getting 10 amperes? I'm wondering. How did you solve? Ohm's law. So what is the voltage across 5 kilo ohm? What is the voltage across 5 kilo ohm? Minus 2 volt. Okay. So, so okay. So 0 minus 2 volt is the voltage difference across current, which is equal to current into resistance, right? Agree? Sorry, 0 minus minus 2 volt. So it will be 2 volt. Right? So voltage across the resistance is 2 volt, which is equals to current into resistance which is 5 kilo ohm. So what is the value of I? 0.4, right? 0.4 milliampere, sorry. You have multiplied both and also missed the kilo term. Yes. So now the current through the bottom 5 kilo ohm resistor is 0.4 milliampere. Can you tell what will be the current through the top 5 kilo ohm resistance? What will be the current through the top 5 kilo ohm resistance? Or can we not get? We need any additional information, or what will be the current through the top 5 kilo ohm resistance? Any idea? 0.2. Parvatam says 0.2. And why is it 0.2? And do others agree with her? Hello. Okay. Let me ask you one thing. What is the current here entering the positive terminal of the open? What is the current? Zero. Yes. Very good. So this is zero. And what is the current in this path entering the negative terminal? Zero. Zero amperes. Okay. Now can you tell me what is the current through 5 kilo ohm? The top 5 kilo ohm? 0.4 milliampere. Yes. So if I draw, the same current is flowing, right? So now let me apply KVL or KCL. So I can say that 1 minus V0 by 5 kilo ohm equal to 0.4 milliampere. So can you guys calculate and let me know what is the value of V0? What is the value of V0? Minus 1 volt. Yes. So V0 is nothing but minus 1 volt. Others are getting the same answer. Okay. So V0 is getting is coming as minus 1 volt. So let us quickly cross check whether it is matching or not. So V0 is minus 1, so it is perfectly matching. So is this question clear? Basically, we have used that virtual short concept and then got this voltage 1 volt. Once we get this voltage, we are calculating the current through the 5 kilo ohm. And once we are calculating the current through this, we know that the same current is flowing through 5 kilo ohm, this 5 kilo ohm as well. So then we have applied the Ohm's law for 5 kilo ohm and then we got the voltage we want to be minus 1 volt. So is this question clear? Can we proceed to the next question? Any doubts, or uh, are you getting the same answer or different answer? Please respond. Clear. Okay. So let us solve another problem. Let us solve this problem. This is also very interesting problem. So this problem and this problem both are exactly same. If you see, only some changes are there. So I'm going to solve one, and we can skip the other because there are plenty of other models. So let us not waste time on the same type of model. So you tell me which one to solve, question 2 or question 3. So whichever question gets more votes, then I'll proceed with that. Question 2 or question 3. Basically, both are same. If I solve one, you'll be able to solve the other one. So Parvatam says question 2. So we have one vote here and no votes here. What about others? Which question you want to solve? 2 or 3 or no vote? Nandini says 2. So then I think we'll have to go with 2 because there are. Okay, what about others? There are 2 more people not interested for voting. Okay, let us solve question number 2. So this is our question 2. So any thoughts how we are going to solve this or what we can do, how to solve, like some thoughts, say we can solve this like this or how to proceed. No ideas? Okay. So maybe I'll ask you few questions, then maybe you'll get an answer. So what is the current through this path? Maybe one input grounded, but we will not use superposition. We'll solve it as it is. And because superposition again, it will become a little bit complicated. We have to solve the same circuit twice, but which is not needed. That's why we'll not do superposition. We can actually do superposition, but it is lengthy. That's why we'll not do. So what is the current in this direction? Says 0. So this is 0. And current in this direction? 0. People are saying 0. So this is also 0. So now I'll ask you another question. What is this terminal voltage? This terminal. This terminal voltage. 5 ohm. Okay. So now, if I say this voltage, let it be VA. Can you solve for VA? And how can you solve for VA? I need voltage VA because I know that if that is VA, this is also VA, right? So I'm always trying to use that virtual short concept and trying to find that V plus or V minus. Any voltage I can find. But here I felt that V plus is easy to be obtained. So that's why I'm asking you. So KVL. So people are saying KVL, or you can apply KCL also because the current in this direction is same as current in this direction, right? So can you apply KCL and tell me what will be the equation? VA equals to 13 by 3 volt. Jnanendra says 13 by 3. What about others? Can you tell me the equation? The KCL equation? You have to be quick. These are easy problems, so you have to be faster. Just asking KCL equations. So Nandini says 3 minus VA by 4K equal to VA minus 5 by 2K. Very good. So Gyanendra says 3 minus VA by 4K equal to VA minus 5 by 2K. Very good. So 3A minus 3, sorry, 3 minus VA by 4 kilo equal to VA minus 5 by 2 kilo. So can you solve for VA and let me know what is the value of VA? 13 by 3. Nandini says 13 by 3. Gyanendra already said 13 by 3. So VA is 13 by 3. So VA is 13 by 3. This is also 13 by 3. So now how can we calculate V naught? How can we calculate V naught? Anyone? How can we solve for V naught? VA minus V0 by 2. Okay, that will give me the current, right? But how can I solve for V naught? How will I know the current through 2 kilo? KCL. Yes. Nandini, you are right. We'll apply again KCL. So now what we'll do is this current is same, right? The current is flowing like this, and this current through 3 kilo ohm is same as current through 2 kilo ohm. So now again we'll apply KCL at this node and we'll get. So Gyanendra says 5 minus VA by 3K is VA minus V0 by 2K. Very good. So let us do that. 5 minus VA by 3K is nothing but VA minus V0 by 2K. I know VA. I am trying to find V naught. So please solve for V naught and let me know what is the value of V naught. Someone says 5.667. Let us see if everyone is getting the other same. Is it 5.667? Everyone is getting the same? Because I was getting a different answer. Kindly check your calculation once again. Yanendra and Parvatam and Avinash, what answer are you getting? V naught. So I can see that 5 minus VA is positive. So VA minus V0 should be positive. So from that logic, I can say that V naught will be less than 13/3. So V naught will be less than 5. So I think you have made a mistake. Kindly cross. 3.888. So Gyanendra says 3.888. So V0 is 3.8888. Nandini, kindly check if you are getting the same answer because this is matching with mine. And we notice 3.888, 3.888, which is also in the range that is given. So our we notice 3.888. Yes, Parvatam also says 3.88. So basically, what we have done here is in this complex circuit, first we have identified current will not flow through this, current will not flow through this, and this voltage are same. So first we tried finding out this voltage VA by applying KCL at this node. After that we got VA, we also got this voltage which is also same as VA. Then in order to find V naught, we have applied KCL over here to get V naught. So all these problems are simple. Basically, you have to apply uh, the virtual short and then solve using KCL. Simple, very simple. All the problems are simple. So any doubts until this point in this question, these two questions? Okay. So if we see this problem becomes much simpler because now this voltage is easily obtained. It is 1 volt, right? Because this is resistor divider. Here it is connected here. So now here it is 1 volt. Here it is 1 volt. So you have to basically apply KCL here and then solve. So this problem is much simpler compared to this. But now that we have solved this, I'm pretty sure you'll be able to solve this also. We'll see if we have time, then we can come back and solve. But now let us not waste time on that. But there are multiple other interesting problems, so we can solve them. Okay. So this becomes our question 3. Okay. So any idea how to solve? Any initial thoughts? Any guesses? All the problems are based on two things, virtual short as well as KCL. So you have to think from that point of view and then you will get the answer. No idea? No? Avinash, Yanendra, Parvata, Shamita, Nandini, how to proceed? Okay, so someone mentions V not equal to minus 1.7, right? But let us go step by step. So how did you solve? Yanendra?
Sir, since the positive terminal is 0, so
Okay,
the negative inverting terminal will also be 0 by applying
very good.
KCL.
Okay.
4 volt minus 0 upon 4 plus 3 volt minus 0 upon 4 equals to 0 minus V out 1 kilo ohm equals to we will get 1.75 minus of
Yes,
that.
yes, very good. So what basically he's saying is current flowing like this and current flowing like this and assuming current flowing like this, he applied KCL at that 0 volt and then he got the expression. So can anyone else tell me what will be the equation of KCL for this case? First of all, this is 0 volt because of the virtual short. And then also there is no current flowing in this, which is also known. So current is only flowing through 3 paths. and then current entering equals to current leaving, which we know from the KCL. So what will be the equation for KCL?
Four by 4k plus 3 by 4k equal to
3 by 4k equals to
0 by 1k. 0.
0 minus V0, right? Right?
Yes. Sir.
Okay, now can you solve for V0 and let me know what is the value of V0? And this is minus 1.75, and they're already said minus 1.75. So we know this minus 1.75. Just others, please cross check and let me know whether you are getting the same answer or not. In the meantime, I'll cross check if it is in the range. Yes, so it is in the range of the answer minus 1.75. So basically what we have done is we have till now we have only used two things for solving all the problems. One is first virtual short, because this is zero, this is also zero, and also we know the input current is zero, so this is 0 volt. And then we have applied KCL. Current entering is equals to current leaving. So current entering is 4 minus 0 by 4k plus 3 minus 0 by 4k, and current leaving is 0 minus V0 by 1k. And by solving this, we got V0 is minus 1.75. So is this clear for everyone? How we are getting minus 1.75?
Sir, how 0 volts are there?
Because of the virtual short, I think you have missed what we were discussing. So in the case of ideal op amp, the negative terminal as well as the positive terminal, which we have represented by V2 and V1, they will be equal. And this is because of virtual short feature or virtual short property. So this plus terminal and minus terminal of the op amp will be at the same potential, and this is grounded. So this is also grounded. So this will be at 0 volt.
For every op-amp circuits,
Yes,
it's
actually ideal open, but in this course, as they're considering ideal open, it will be yes.
okay.
Also, it should be negative feedback, but that you will not know at this point of time. So every negative feedback op-amp will have virtual short, but you don't know what is negative feedback. But in this course, all the op-amps are connected in negative feedback fashion. So you can blindly consider this and this are virtually short, because that is there in the syllabus of this course. But you will in the future know that this virtual short will only happen when there is ideal op-amp as well as negative feedback. That you will like get to know later, but it's okay. For this course, you can blindly consider. So now we have solved this problem. Let us quickly solve this problem. Okay. So how to solve this problem? This will be our problem.
4 by 4k equal to 3 minus V0 by 2k.
Very good. So basically, you are saying the current flowing through this will be same as the current flowing through this. So from that you got 4 minus 4 minus 0 by 4k is equals to nothing but 3 minus V0 by 2k. So what is the value of V0?
One volt.
1 volt. Very good. Others agree? Yes. So what about others? Yanendra says yes. What about others? Nandini, Parvatam, and Avinash. Yes. Okay. Everyone is saying yes. So like now, if you see, the things have become very simpler because we are just directly using this virtual short mechanism as well as the KCL. And now things are becoming easier. And I think now you will also be more confident to solve these problems. So this problem we have just solved. Let us cross check the answer. It is 1 volt and it is perfectly fine. So it is 1 volt. So now let us solve this problem. This will be your problem 5 for today. So how are we going to solve this? What is the value of V0? Any idea, anyone? How to solve, how to proceed?
V2 and V1 are 2 volts.
Okay. So you are saying that this is 2 volt. So this is also 2 volt. Okay. After that, how are we going to proceed?
In that node also 2 volts.
Which node? This node.
Between 4K and 2K. Yes.
This is also 2 volt. How is it 2 volt?
Same voltage is also connected.
But in between there is a voltage source, right? The voltage source value is 2 volt. So how can both the terminals be at 2 volt? So Gyanendra is saying minus 2 volt. What about others? This simple question, I am not sure why you people have so much confusion. So we have a voltage source of 2 volt. Left terminal is at 2 volt. What will be the voltage of the right terminal? Nandini says 4 volt. Okay. We have so many answers, but not the right answer. Okay. We have a voltage source of 2 volt. The positive terminal is at 2 volt. What will be the potential at the negative terminal?
Minus 2 volt.
Okay. Like we are in the last week of the network analysis and you are like still confused with the basic KVL. Okay, so now I'm calling this as VA. I'm calling this as VB. What is VA minus VB?
Four volt.
But how much it should be?
2 volt.
So where we are
Zero. Zero.
0, right?
Yes.
Yes, right. So it is 0 volt. Everyone agree? Should be 0, right? Because the left terminal is at 2 volt and the voltage source is 2 volt. So the right terminal should be at 0 volt. You can also do like this KVL. We are going from higher potential to lower potential. So minus 2 volt, 2 volt minus 2 volt, 0 volt. So it is simple. Okay. So how to solve for V naught now? 4 volt. So Parvatam says V naught is 4 volt. Okay. Others, how to solve for V naught? Any idea?
Zero by 2k equal to V naught by 4k.
Yes, very good. So you are basically applying KCL because you are telling that this current is 0. So basically you are considering the current to be flowing in the downward direction. So you have applied KVL or sorry KCL. So you are saying V naught minus 0 by 4k equal to 0 minus 0 by 2k. So what is my V naught? Everyone?
2.
How much?
2 volt.
Are you sure?
Zero volt.
0 volt. Why are you making so many mistakes? We are at the end of the course. Huh? 0 volt. So let us go and cross check whether our answer is correct or wrong. So it is 0, directly 0. So the answer is 0. Okay, so what we have done in this question is again same thing, virtual short. See, all these problems are very simple. Unless you make a mistake, you will not lose marks. So I am expecting you should be able to score 100 out of 100 until you make very silly calculation mistakes. Else it is very easy and you can see, right? We have already solved 5 problems and we have around half an hour or 40 minutes left. So we can solve probably another 4 to 5 problems. Basically what we have done is it is virtual short. So this is 2 volt, then this becomes 2 volt. If this becomes 2 volt, this will become 0 volt. So if you make mistake here, your answer will be wrong. And now that this is 0 volt, basically no current is flowing in this and no current is flowing in this. So no current will flow in this. So V0 is nothing but 0 volt. Or you can apply KCL to get V not equal to 0. There is less than a minute. This meeting will end soon. And once this meeting ends, kindly join back. We'll solve a couple of more problems. I think we can solve another 4 to 5 problems. So any doubt until this point, until these 5 questions?
Sir,
Anyone?
without going to that equation, we'll tell everything is 0 volt. So current is also 0. So V naught is 0.
Yes. We no need to apply KCL also.
Yes.
Okay. Let us solve a couple of more problems. So just now we have solved this and we got answer 0. Now let us solve this. Okay. How to solve this problem? So this becomes our problem 6. How to solve this problem?
Zero volt, sir.
Okay. How is it 0?
V naught resistance is 0, sir.
We know.
Resistance connected. There's no resistance for V naught.
Okay. But how can you say that if there is no resistance, voltage is 0? Okay, let me ask you one question then. What is this voltage?
Three volt.
How?
One plus two connected to positive terminals.
This voltage, I'm asking this voltage. So Gyanendra says V naught. So what about others? What is this voltage? Do you agree? Is this V naught or not?
0.
How is it 0? How is it 0?
For previous problem, you said if it's V naught, then the other terminal is 0. For 2 volt.
Here we are getting 0, right?
Yes, sir. You said if one terminal is 2 volt, then the other terminal is 0.
Why is it 0 again?
Because 2 volt is connected across it.
So if this is 2 volt, this is 0 volt, right?
Yes, sir. Then
If
only
this
we
is
will
3
get
volt,
VA minus.
if this is 3 volt, what is this voltage?
Then at left side it will be 3 volt and
Right side?
then 0 volt.
Right side 0. Now I'm saying if the left side is 3 volt, what will be
Right
the
side
right
is
side?
1 volt.
1 volt,
1
right?
volt.
So
Yes.
now here, how are you saying it is 0 volt? Based on what you are saying 0 volt?
Okay, so I got it, sir. That term is also V naught.
Yes, this term is V naught, right?
Yes.
Okay. Now what is this voltage?
V naught.
And what is this current?
What's it?
This current, input current. 0, because maybe you might have missed. So for the op amp, the input resistance is infinite. So as if there is open circuit at the input. So the input current of an op amp is 0. So that's why always the input current of an op amp is 0. Okay, so now how to solve for V naught? Now how can we solve for V naught? Apply KCL and equate to 0. Yes. So Gyanendra says it. We'll apply KCL. So current entering plus current entering equals to 0, right? Because uh, we are applying KCL. Current entering equal to current leaving. Current leaving is 0. So what is the equation for current entering? Sir, no feedback, then the output is 0. This is the feedback, no? I'm not getting how you are saying V naught is 0. I didn't get what you are asking. Okay, maybe just to clear your confusion, I'll add one more circuit here, non-inverting differential amplifier. So there is also called as another circuit, buffer, unity buffer or buffer. So what happens in this is, this is plus, this is minus, this is VI, this is VO. By virtual short, you can directly say that VI is VO or V not equal to VI. So this is called unity buffer or buffer. Clear? Just virtual short. If this is VI, this is VI, which is equal to V naught. So VI equal to V naught. Okay, now let us go back to our question. Okay, now how to solve for V naught? Is it the same as voltage follower? Yes, voltage follower. Yes. But for op-amp, it is called as buffer. Yes. In the case of BJT or MOSFETs, they call it voltage follower, emitter follower, something like that. So, okay. How to solve for V naught? Anyone? No one? We have to apply KCL. So, what is the expression for KCL?
One minus V naught by 5K
Okay.
plus 2 minus V naught by 5, 2.5K.
Equal to 0. Yes. Very good. So, now solve for V0. Okay, Gyanendra says 1 minus V0 by 5K plus 2 minus V0 by 2.5K equal to 0. Very good. So now solve for V naught and let me know. So V naught, you are saying it is 12 by 7. Can you convert it to decimal and let me know? 12 by 7 is how much in decimal? I'm not sure how you got 12 by 7. I think you might have made a mistake. It will not be 12 by 7. Just kindly cross check.
1.66 volt.
Yes, very good. So V naught is 1.66 volt. Gyanendra, are you able to get the same answer? 1.667.
Sir, whether we should stop up to 3 decimal or 2 decimals.
Sometimes they'll mention, let us see. They have not mentioned. So then you can go to 2 or 3 decimal, but better be 2 decimal. I'm not sure. Usually in the assignment that we create, we'll mention up to 2 decimal. Now that they're mentioning till 3 decimal, better you mention 3 decimal. So our V naught is 1.667. So it is also within the range. Okay, so our V naught is 1.667. Okay, so basically everywhere we are doing the same thing. Virtual short and then KCL. Virtual short, KCL, and input current is 0. So these three only we are using. Okay, let us solve another problem. This is what we have solved just now. Let us solve this. Okay, so this will be our problem 7. So how to solve this problem?
4 volts V1.
Okay, so you are saying this is 4 volt. So this is also 4 volt. Okay.
Then 3 minus 4 volt. 3 minus 4 divided by 4K equal to 4 minus V naught by 8K.
3 minus, 3 minus 4 by 4K equal to 4 minus V0 by 8. Okay, very good. And what will be the value of V0? Calculated that will.
6 volts.
6 volts. Very good. Let us wait for others. 6 volts. So Parvatam and Gyanendra also say 6 volts. So this problem is very simple problem. What we have done is we have used the virtual short concept because this is 4 volt. This will also be 4 volt. And then the current through this is 3 minus 4 by 4K, which will also be the same as current through this 8K, which is 4 minus V0 by 8K. So we have equaled both of them, and then we got V0 is nothing but 6 volt. So yeah, everyone is saying 6 volts. Good. Now let us solve one more problem. And let us solve this problem. Okay, so this will be our problem 8. Okay, how to solve this problem?
V not 2 volts.
Okay, and how did you get it?
1 volt, 1 volt plus 1 volt 2.
Yes, very good. So V naught is 1 volt plus 1 volt, which is 2 volt. Very good. Okay, so let us cross check whether V naught is 2 volt or not. So V naught is perfectly 2 volt. So it is correct. So now others agree with this, whether you are following whether we are getting V naught equals to 2 volt or not. Yes. Okay. So now I have another question. I am going to ask what is this current? So this current is I. What is the value of I? So can you please calculate and tell what will be the value of I? So you solve for I and then let me know what is the value of I. So this is not asked in that question, but I am asking you. What will be the value of I? So Nandini says minus 0.166 milliampere. Let us wait for others whether they are getting the same answer or not. Then I'll let you know the answer. Yes. So Gyanendra also says minus 1 by 6K. Okay. What about others? Are you able to get it? Maybe I'll wait for 1 or 2 more minutes. Just give it a try. Then I'll tell the solution. Okay. Maybe I'll give a hint. What is the current through 6 kilo? What is this current? Sorry. What is the current through 6 kilo? Shamita, can you tell me what is the current through 6 kilo? 6 milliampere. So Parvatam says 6 milli. How is it 6 milli, Parvatam?
1 by 6K.
Yes. So 1 by 6 milliampere, right?
Yes.
So now can you tell me what is the value of I? Okay, everyone, what will be this current?
0.166 milliampere.
Plus or minus?
Minus.
Okay. So basically this current is 0. So if we apply KCL, then we'll get I is minus 1 by 6 milliampere, or I is minus 0.166 milliampere. Okay. Everyone get it right? How we have solved for I, which is minus 0.166 milliampere. Agree, everyone? Can we proceed to another problem? Yes. Okay. So let us solve one more problem. This problem. Okay. So in this problem, how to solve for V naught? This will be our problem 9. How to solve for V naught?
1 volt, sir, for the
Which is
minus terminal,
which is 1
negative
volt?
terminal.
Okay, this is 1 volt. Then how to solve for V naught? Anyone?
1 by 5k minus 1 by 4k equal to V naught minus 5 by 6k.
No, I didn't get it. Which currents are you equating? Okay, first of all, is this current 0? This current is 0, right?
Yes, sir.
So now I can equate this current as well as this current, right?
Yes, sir.
You have to keep in mind one thing, that this current is non-zero. Output current is non-zero in open. Only input current is 0. So there you cannot apply KCL because this current is unknown. You cannot do that. So Gyanendra says 0.25. Let us see it is correct or wrong. So now if we apply KCL, what is the current that we are getting? Through 5K and 4K, both are same, right? So what will be the expression? So Gyanendra says V minus 1 by 5K equal to 1 by 4K. Very good. So we have V0 minus 1 by 5K equal to 1 volt by 4K. So now what is the value of V0? 2.25. So Gyanendra says V0 is 2.25 volt. Very good. Now we'll ask another question. What will be the current through this 6K? What is this current I? Others agree? How we got V naught as 2.25? Okay, let us quickly cross check whether the answer is correct or not. 2.25, so it is in the range. It is correct. Yes, so Nandini says yes. So now can you please quickly calculate and tell what is the value of I? Okay, Nandini, Parvatam also says 2.25. Very good. So what will be the value of I through 6 kilo ohm? Current through 6 kilo. Anyone?
Minus 0.46 milliampere.
Okay, minus 0.46. Parvatam says 0.48. Okay, let us quickly cross check. I have not solved, so I am solving. I is nothing but 2.25 by minus 5 by 6k, right? So I is nothing but minus 2.75 by 6k. So how much are you getting? Minus 0.4. Shamita, how much did you get? Minus 0.4.
46 milliampere.
Okay, 46 million. So I hope everyone is getting the same answer. Yes, sir. Okay, Nandini says yes. So basically, we have solved in this problem V naught, and then we have also solved for I, which they have not asked in this problem, but I have asked you so that maybe in the final exam they can ask. So we have solved all the problems, and now that we have time, let us solve this problem that we have missed, which will be our problem 10. So now this problem, I'm not going to give you any hint because similar type of problem we have solved. So you tell me how to solve and let me know what voltages you are calculating and how you are calculating. So this will be our 10th problem today. So how to solve this? They're asking for
Sir,
V naught.
in
Yes.
previous problems, sir,
Okay.
I have a doubt.
Yes.
Here, both how you are telling current is going downwards.
I am
Here in
asking,
this across 5k ohm and 4k ohm.
you can consider in any direction. Basically, I'm applying KCL, right? So it doesn't matter. Even if you consider from bottom to top, the equation will remain same, right? Or will it change if I consider from bottom to top?
In previous problem, you said current. No, sir.
Which problem? This problem.
Before that, sir.
Okay. This problem.
I
This
forgot
problem.
which here only.
Okay. This problem.
You said current goes minus in opposite direction. At node, one direction, another the direction.
Which question I'm not getting? Like I'm not getting your query. Okay, let us go back to this question and now tell what is your query. I didn't get.
How you telling that down directions?
It can vary even if you consider from bottom to top. I'm asking with the answer change, like we not change. Like if you consider say current is flowing from bottom to top and write the equation for KCL, you check and let me know whether V not will change or not because it is not direction dependent, right? I'm basically applying KCL. I have to consider one direction and I have to apply the KCL for that direction. So if you consider bottom to
You
top,
applied KCL at which node, sir?
1 volt, the 1 volt node I have.
Okay.
So that's why V0 minus 1 by 5k current entering equals to current leaving, right?
Okay, sir. Yes, sir. I got it.
So now in this problem, how to solve? Anyone? Because we have solved similar type of problem and that is a little bit more difficult. Also, I have given a hint for this. So how to solve this problem?
What's the hint, sir?
Uh, that I have given them, but now that I have not given you, can you think and tell? Because I want you to try without it. Then if you cannot, then I'll give you more. So how to solve this problem? Others, don't try to solve, just let me know how to solve so that others can also get time to give it a try. No idea?
At negative terminal, 0 volts.
Okay, how is it 0? So Gyanendra says find VA equal to VB and he's saying 1 volt. So how you are saying here it is 0? Okay, Gyanendra says VA equal to VB equal to 1 volt and then apply KCL. Okay. So I'm asking you what will be this voltage? One volt. Parvatam says 1 volt. What about others? What is this voltage? Others? What about others? Gyanendra said already 1 volt. Avinash, Nandini, and Shamita.
How 1
1
volt?
volt. So this current is 0, right? So basically now it has become a resistor divider, right? So this is nothing but 2K by 2 plus 2K into 2 volt, right? It's a resistor divider, right? Right? It's a resistor divider, right? 2K, 2K are in series and the supply is 2 volts. So both will carry 1 volt, 1 volt. So this middle voltage is 1 volt, right?
Then across that it will be 0 volt, sir.
Which across which?
Across positive terminal, that line.
Which line? This line.
So the
No,
2 volt will be taken by 2K, only both the 2 cases. Sir.
1 volt each.
Okay. Sir.
Okay, so now what will be this voltage?
Zero volt.
Why? Parvatam also says 0 volt. Why it is 0 volt? And how is it 0 volt? Shamita, how is it 0 volt?
If one terminal is 2 volt, then other terminal will be 0.
So basically, it is positive terminal is at 1 volt. So minus terminal should be at 1 volt, right? Virtual short, right? Plus terminal is
Yes,
at 1
sir.
volt. So this will be at 1 volt. So now apply KCL. So this current will be equal to this current, right? Because current in this direction is 0. So now what will be the equation for KCL?
Two minus 1 by 1K equal to 1 minus V naught by 4K.
Now can you calculate and tell me what will be the voltage of V1?
Minus 3 volt.
Very good. So basically the same thing we have done. First we have calculated one of the positive and negative terminal voltage, apply virtual short property and then apply KCL and then we got V naught as 3 volt. So minus 3. So V naught is minus 3 volt. So any queries in this problem? So we have solved quite a number of problems today. But one thing I have noticed whenever I'm asking questions, you are not trying to understand the concept and find the answer rather than you are just predicting it 1 volt, 2 volt, 0 volt. With that, it will not work. Like if you know, then you have to see how you have to calculate that voltage and tell. If you don't know, then you have to understand or try to ask how to do. You are just like just throwing stones, saying 2 volt, 1 volt without understanding the concept. So if you try to do that, then you'll not be able to solve anything in the exam. You should understand the concept. If you understand, then you have to apply it. If you have not understood, then you have to try to understand the concept. But just by guessing, giving random guesses will not help. You have to understand what exactly am I trying to do in each of the problem. I have applied the same concept in all the problems, and you should understand how I am doing that, and you should try to apply the same. And if you face any difficulty, you should ask like you have not understood. But I have seen that you are just trying to give some random guesses without thinking, and that will not help you in the exam. Because here I am telling you that you are wrong and this is the right. If you do the same thing in the exam, you will lose marks. This is a very easy week. If you try to understand the concept easily, you will be able to score good marks. And that's why I have solved more number of problems. And yeah, like please try to understand. If you have not understood, I will be uploading this video in the YouTube. You can go through it and understand and solve also the same problems by yourself without looking the solution. And then try to understand what exactly I'm doing. Also, there will be another 1 hour session on this Wednesday from 7 to 8 p.m., which is like a summary session. Or if you have any doubts, you can ask. I'll try to summarize whatever we have discussed in this 12 minutes. So with that, I'm going to conclude this session here. If you have any questions, you can ask, else I'll end this session here. Any doubts?
Sir,
Thank
to
you so much.
solve this week, to solve this week problem, the basic concepts of which was short and incoming current is 0
Zero
and
and
out.
KCL. Yes.
Okay, sir. That's all, sir.
Yes, that's it. You have to apply it properly without making mistake. You will again able to score 100 out of 100 in this week also.
Okay, sir. Thank you, sir.
Yeah. Okay. So Gyanendra says thank you, sir, and Narendra says thank you. Yeah, thank you all. It was a very nice interactive session, but don't try to make any silly mistake. You will lose marks. Try to score as much as possible in this week to compensate for what you have missed in the earlier weeks. So with that, I'll conclude this session. Yeah, Avinash, thank you. And I wish you all the best for your week 12 last week. There will be another session day after tomorrow. You will get a mail probably tomorrow. So try to attend that. That will be a summary session. And I wish you all the best for your week 12. See you again on Wednesday. That will be probably our last communication. Yeah. Okay then. With that, I'll wind this session up here, and I wish you all the best for your week 12. Good night.